Alright class, second last lesson. We've got lesson 8, which is quite similar to our previous lesson on resonance with strings. Today we're looking at resonance with air columns. And in many ways they're very similar. There are some important differences though. So air, just like strings, has many natural frequencies. These are dependent on, again, the length of the pipe or the air column and other parts of the air. And while we're going through this, I'd like you to keep in mind that air is a longitudinal wave and we've got particles in the air. So when we see these peaks and these troughs, that's going from regions where we have lots of air molecules, compression, high density, and then areas of rarefaction, low density. So we're going to model it with a transverse wave, but it's kind of nice to keep in mind that air actually travels as a longitudinal wave. All right, so when our source vibration, and we can have lots of different forms of that, we can have vocal cords of somebody singing or even talking. We can have, they're called tuning forks, and you can ring them and they will vibrate at a certain frequency. So the source vibration would be the ringing or the vibrating of that tuning fork, right? Even the vibrations of the air blowing across or blowing through a flute or a recorder or any wind instrument like that will produce these compression waves as the air passes through and rubs against the roughness of the holes and the surfaces, and those vibrations as it's passing through will create these vibrations, and as a result we can have resonance if we're matching up with the natural frequency of the air. So it kind of depends on the air you're in and the instrument you're working with, but there will be certain frequencies that resonate, and just remember that resonate means that we're increasing the amplitude, making it louder with a higher amplitude, and that's because our periodic force or our vibration, source vibration, that could also be known as our periodic force, will be matched up with the natural frequency of the air. So this is going to look pretty familiar, very similar to strings. The big difference right away that lots of you will see is we're no longer working with half a wavelength, but a quarter of a wavelength for our natural frequency. And that's because the air will never have a fixed end at this one open end. What I mean is we won't have a node. Here's our node at a fixed end at the close side of our air column, but at the open end, the air will always have an antinode when it's resonating, because there's nothing holding the air, nothing for it to fix to, right? And that can further be identified by seeing that all even harmonics are impossible, right? We can't have a node at the open end. There's no way, there's nothing for the air to fix onto and form a node. The air will always be an antinode at the open end of our air column and a node at the fixed end, right? You can still have nodes midway through, but it's important to see that the open end will always form an antinode. So an air column closed on one end, that's what we consider a closed air column. And you will see later that we can have two open ends, but here with one closed end. So this would be like, I'm sure most of you have done at some point in your life, blowing into a bottle and hearing that sound that it makes, right? Because we're going to blow our air into the bottle. It's going to form a node at the bottom of the bottle, and then as it comes back out, we'll have an antinode, and it will be resonating if it is in that fundamental frequency, right? We have one node, one antinode. So fundamental frequency is the lowest natural frequency of the air column, our F0 or F1, and we're only creating a half loop. So that's the big difference with strings and closed air columns. Only a half a loop is created by the fundamental frequency, right? So second harmonic is impossible. This doesn't exist, right? Impossible. If it were theoretically possible, it would form a full loop, right, with a node on each end, but we can't have a node on that open air end. That's impossible. There's nothing for the air to fix to, so you can't have a fixed end. And our third harmonic, N3, will just be very similar to our strings. Instead of one half loop, we have 3 half loops. 3 half loops are created, and it's going to be 3 times our fundamental frequency. And the length is going to be 3 times our quarter wavelength, right, or 3/4 of a full wavelength. Because if we were to continue drawing our wave here, there's half a wavelength, there's 3/4, and a full wavelength would be here, and that would be our fourth harmonic, which is impossible, right? So just have to be able to see where we're at in our wavelengths with these drawings. That's going to be an important part of this. So in summary, if a closed air column, we can only have odd harmonics, 1, 3, 5, 7, so on and so forth. And for the nth harmonic, assuming it's odd, we can use this set of formulas, very similar to our strings, but this is our difference, right? We're working with quarter wavelengths because we're working with half loops rather than full loops like we did with strings. Here we go. Let's try an example. We have a tuning fork, and it's telling us where it's resonating or where it's vibrating. So in this case, the tuning fork is our source vibration. So I'll draw it out to start with. We have a tuning fork. It's one of those things. Maybe you've seen them. And you're going to hit it with a mallet. And when you let it ring, it's going to vibrate at 740 or 68 hertz. So that's going to be our source vibration. And we're holding it over a closed air column, just like a pipe with one fixed end and one open end. The speed of sound they're giving us, V, is equal to 340 meters per second. So speed of sound will depend on lots of parts of the air. So the question should always tell it to you. If they don't, I think you could just write an assumption. But this one tells us. We want to determine the length of the air column for the third harmonic. So how long is it for the third harmonic, or L3? So we're going to start with our universal wave equation because we have a frequency, we have a velocity, we can find a wavelength. So we're going to try to solve for wavelength here. Wavelength is equal to V over F, 340 divided by 768 hertz. Meters per second divided by 1 over seconds gives us meters as wavelength, which is 0.4427 meters, or 44.27 centimeters. So we have to now think about what's going to happen in here. So I'll just kind of walk through our different harmonics we could have. Our first one would look like that. That's really messy. That's our first harmonic. We're not looking for first, we're looking for third. So with third, we're going to have 3 half loops. We're going to have a node here, antinode, node, antinode. So it'll look like this, where we have 1 half loop, 2 half loops, 3 half loops. So we're in the third harmonic for this one. So we're looking for the length of this if we were in the third harmonic. So the wavelength is constant, and we're going to just lengthen the tube. So the wave here is always going to be 0.4427 meters. We're looking for the length of our third harmonic, and we're going to use our formula for closed air column, where it's a quarter or 0.25 of the wavelength times our harmonic number. So the third harmonic, right, another way to look at this is we don't quite have a full wavelength. We're not quite going to be 44 centimeters. We're 3/4 of it. We would have to have that last half loop, last quarter wavelength. So this is the way to use the formula. 3 times 0.25 times our wavelength, which was 4427, which is coming out as 33.2 centimeters. All right, another just quick way to do this would be to take our wavelength, multiply it by 3/4, right, or 75% of it, because we have 3/4 of our full wavelength. All right, that's essentially what we're doing here with the calculation. All right, now we want to determine the next resonant length. So let's think about this. If we went one half loop more, we would have this waveform in our closed air column, and that is impossible because we have a node at the open end, right? So this would be our 2, 3, 4th harmonic, and if we remember from our notes, any even harmonic is impossible, right? This proves it. So instead, I'm going to go to my next possible harmonic, which is my 5th harmonic, right? So I'm going to have 5. So what's really happening here is I'm lengthening my pipe, right? I'm not actually squishing my wavelength, because the wavelength of the sound in this air with this frequency is always going to be a constant 44 centimeters. Right, so I've lengthened it. This is going to be my L3 would be to the bottom there. L5 is going to be a little bit longer so that we can fit that extra half wavelength in. So I'm in 1, 2, 3, 4, 5. This is my 5th harmonic, and I can calculate the length of the 5th harmonic by using my n times a quarter of our wavelength. So n is 5, quarter of 44.27 centimeters gives us 55.3 centimeters, which makes sense because this would be a full wavelength plus a quarter. So full wavelength would be 44. We're going to add an extra quarter wavelength to that and end up with a length of our pipe being, or open air, closed air column, one side closed, one side open, 55.3 centimeters. Okay, moving on to our final type of resonance. We've got open air columns. So with an open air column, we now have 2 open sides. This would be like, a recorder, I think, would count as this, or a flute, because you technically have 2 open sides. So you'll see we have 2 antinodes on either side. We can't have a closed end with a node, right? We'll always have 2 open ends, 2 antinodes. Antinode, node. antinode. And it's impossible to have two antinodes, two open ends, without having a node in the middle. So our fundamental frequency is going to be our antinode, node, antinode, which ends up being half of a wavelength, a quarter plus a quarter loop. So this is most wind instruments, tubes open at both ends. Even if they're not fully open, they'll still have a slit for the air to come out at both ends. So the fundamental frequency is the lowest natural frequency of the air column again, and we're creating two half loops equating to one full loop. Don't get this idea of loops and wavelengths confused, because still here we only have half a wavelength. So it's very similar to a string. The difference with the string is our string would look like this, right? Where we have a node on each end instead of an antinode on each end, but it's still the same half wavelength, right? It's kind of like a sine graph compared to a cosine graph, only half of a period. Second harmonic, we're going to form four half loops. Again, similar to our closed air column, we need to have antinodes at each end, so we won't have any actually, this is the second harmonic. So we've got 1, 2, 3, 4 half loops, or one full wavelength. So unlike closed air columns, all harmonics are possible. We're just always starting with an antinode on each end. But you'll kind of pick up on the fact that as we go up by our harmonic from first to second, we're adding another node, right? So the number of nodes actually corresponds to our harmonic number, whereas with a string, the number of antinodes corresponds with our harmonic number. Hopefully that didn't confuse you more. So second frequency again is 2 times our fundamental frequency, and we've got 2 times our half wavelength, so full wavelength, right? Starting, that would be half, that's a full wavelength, peak to peak, crest to crest. So in summary, open air columns are similar to stretched strings. We're just switching our nodes and antinodes around. And at the nth harmonic, we're going to use the same set of equations that we would for our strings. Okay, no example for open air columns because it's so similar to strings, just some subtle differences that you're going to need to keep track of. All right, good luck with the homework. Please let me know if you have any questions, and I will talk to you later with our last lesson of the year. Woohoo! See ya.